Yeah.
Yep. So hello. Yes, indeed. My name is Orpheas, and so I'll be presenting you a substructural type and effect system. This work has been done also in collaboration with Robert Krebers. But okay, the key takeaway that I want you to have by the end of the talk is that if you have a thing called references and you have effect handlers put together, it's a lethal combination. Okay. But if you don't know what references are and what effect handlers are, don't worry, because by the end of the talk, you will know what they are. So let's start with references, specifically deallocatable references. And look at this code here, which is kind of like Haskellish, but it's also impure because we have references. So the way you should think about references as some kind of like pointers in C. So it points to some kind of a memory location, and you can allocate a reference with some kind of value in it. And you can free references. You can read from the references. And in this code here, this foo code, we allocate a reference and we bind the reference to X. And then we call this bar function X. We don't know what it does. I'm not giving you, it doesn't matter. And then based on the result of bar, we're either going to free X or we're going to read from the reference. And the question here, what can go wrong in this nonsensical piece of code? And well, the question to ask here is, what if bar itself frees the reference? Because it gets it as an argument. What if it frees it? And if it does, actually, we can have two problems might arise. We can either get a double free, because if bar returns true, then we do a free, bar itself gets a free, and then afterwards we also going to do a free. Or we can, if bar does a free and returns false, then we also going to use we read from it as well. So we get a use after free. And these two problems, this double free and use after free, are very big problems. For instance, this is a February 13th, 2025 problem, news story. Google has paid out $55,000 to part of its bug bounty program for a use after free vulnerability to the JavaScript V8 engine. And not just Google, but this use after free, double free errors are pervasive. They are the source of highly security critical exploitations, and for instance, in the Linux kernel, in OpenSSH, Apple iOS, SQLite, Firefox, Windows, everything. Because when you talk about native applications, usually written in C, C++, you have this kind of like freeing and allocating for reason. You have this manual memory management, and then this sort of bugs, these use after free, these double free bugs arise. And as soon as you get this as soon as you detect such kind of an error, then you can exploit it, and lots of bad things will happen. So the problem here is that we have a language where there is a way to do these invalid memory operations, such as some kind of like more low-level languages. You can get this use after free, these double free errors, which are the source of very security critical bugs. So what is their solution? What is one solution that I'm going to give in this talk will be to give a compiler, make a compiler detect and forbid this kind of invalid memory operations. And the way I'm going to present is the solution is using a substructural type system that can detect this kind of double frees and use after frees and forbid them. So what is a substructural type system? Well, firstly, we should ask ourselves, what is a type, right? And actually, it's not a simple question. Just what is a type? There's lots of, you have your simple types, which you might have seen before, like unit, int, function types, which just tell you kind of like the structure of your variables, the domain of what your variables hold or of your memory locations. But then you have also more fancier types. You have like, for instance, substructural types, which in this talk, I'm going to underline to make it clear that we're talking about some special kind of type. We're going to have a substructural type is going to have a bar underneath it. But substructural types don't just tell us what kind of what is the domain of the contents of the variables of the memory cells, but also how many times we can use them. And here I'm giving you two examples. I give you like a references and the special function types called like a lolly here. Which don't worry, I will explain these things, what they are. But they also tell us about how many times we can use them. So you get like extra data from them. But apart from that, you also get effect types, where effect types you have like, for instance, this function type here. It no longer is just a function type, but it also tells us what kind of effects it might produce. But apart from that, you also have dependent types, you have session types. So what I'm trying to say here is that this, with the question, what is a type, is not a, is quite complicated. But in this talk, I'm only going to focus on these three above, the simple types, the structure types, and effect types. But okay, so this is nice. So types give us some kind of guarantees, tell us some kind of information, but how do we enforce that this, what the type, the meaning of the type, how do we enforce the meaning of the type? And the way we do this is using type systems. So what is a type system? Well, first of all, you can characterize type system as like static, gradual, dynamic, but the way it's just a way to enforce that the meaning of types is obeyed. And usually we want to do this formally. We make some typing rules, such as the apps, the abstraction typing rule. And the way we do it, we have these typing rules and we compose them to get some typing derivations, which are proofs that a type is well typed, and an expression is well typed. But in the case of simple types, we have, you should have like a little bit of an intuition, right, of what it means for a well-typed program when we're talking about just simple types. A true is of type Boolean, sure, but we cannot say that 256 is of type Boolean, or we cannot apply true with 0, right? So it's okay. We have an intuition of what a simple, what the type system should do in the case of the simple types. But with the substructural types, what exactly do we enforce here? So specifically, these two types, these substructural types, what are we, what is the type system supposed to do here? And let's start with the first one, the ref int. And I've told you that before, I gave you this example of like the references, the deallocatable references. If we have allocation and we have freeing operations, then we can get this use after free, this double free errors. And I told you that the solution to this, to forbid this kind of errors, is using substructural types. So the idea here is to treat reference types as substructurally. And what we mean by that is to have a notion, to introduce the notion of affine reference types. And affine means that the type system will restrict our references only to allow them to be used at most once. So if we have an affine reference type, so ref with this underbar, the type system ensures that we cannot use references more than once. And what I mean by that is this, for instance, in the accepted column, we can allocate a reference and then return it, but we cannot allocate a reference and then return a pair where we use it twice, because you can only use it at most once. Similarly, we can allocate a reference and then free directly afterwards, right, to the top left, the second row. But we cannot allocate a reference and then free it twice, because we're using the reference twice. So this type system ensures that we're not able to use the reference more than once. In a slightly more complicated example, we can allocate the reference and then capture this reference in an abstraction. This is like Haskell-ish syntax, like a lambda, which is perfectly fine. But at the same time, we cannot allocate a reference, capture it in an abstraction, bind it to an f, and then call this function f twice, because then we would get the free twice. So that's we're not gaining anything. So in the last case, there is maybe we should ask ourselves here, okay, so what kind of type should we give to f in this case? So f has to be, the type system has to ensure that f is not called more than once. But so it cannot be given like a regular function type, right? Because a regular function type can be called any number of times, but the type system has to ensure that no, this is a special function that can only be called once. Otherwise, all my guarantees that I want, the memory guarantees that I would like to have, all hope is lost. So the question is, what type should we give to f? And the idea is to introduce a new function type called an affine function type, which usually is use this lolly notation. But the affine function type here, the type system knows that, okay, this is a function that has to be treated affinely, so it cannot call it more than once. So whenever we're having with a substructural type system, such as an affine type system, where we want to use things at most once, we also usually introduce another notion of a function type. Okay, so now that you have a little bit of an idea of like intuition of how like a substructural type system, what it's supposed to do, how can we solve the problem that I've given before? And the way to solve this problem is by forbidding the problem. This is not a well-typed program, because if we allocate a reference and then we call bar, we already used x to pass it to bar. We cannot use it again to free x and then to read x. So this is an invalid. The type system rejects this program because it's saying, you're using x twice. You're using, firstly, you called bar with x, and now you also want to do a free with the x. You also want to do a read with x. That's a no-go. That's a no-no. So in actuality, now the type system says that, well, because you're handing out the reference, you're only hanging out, you can only use it most once. Bar is given the responsibility to deallocate x, to use x however it wants to. So in a way, this is a way to forbid this memory errors that I've talked about, this double free, this use after free. And it might seem that this is a very restrictive, this kind of program, because, and it's maybe also not very nice to program with. But this is if you know Rust, for instance, Rust is based on a substructural type system, an affine type system. But there with Rust is much more complicated. You have you have ownership, you have lifetimes, you have all these fancy features to make it more easier to program with. But the core idea is with this, using a substructure, limiting your how many times you can use things from the context. Okay. So now I want to switch to a little bit different. So I've talked a little bit about how to make a language more robust. For instance, a very simple Rust, let's just say. But now on the expressivity side of things, I want to talk about algebraic effects and handlers. And algebraic effects and handlers are more to make your language more expressive. It's a programming language construct that gives you more power. But it doesn't really have to do anything with making it more robust. But what are they in the first place? Okay. So to explain what effect handlers are, I'm going to rely on your intuition, maybe on exception handlers, but I'm also going to give a little bit of an overview. What's an exception handler? Okay. So with exception handlers, with exceptions, the idea is that such language such as in Haskell, in Python, lots of languages have exceptions, but the idea is anywhere in the code, we can just raise an exception to say that, oh, we got an error. We have a exceptional behavior. This shouldn't happen. I don't know what to do at this point. For instance, we can define this add function here, which works on unsigned integers. And the idea is that it will check if the maximum amount, because, you know, like we're talking about finite things. So an unsigned integer has some kind of a limit. And if the maximum value that you can store in this unsigned integer is, if we subtract x from it, this gives us the amount of things that we can add to x. But if this thing is, if y is bigger than this thing, then we're going to get an overflow, is the idea. So then we're going to raise this overflow. It's an exception that, okay, this is like a safe add operation because it tracks whether an overflow happened. Otherwise, if an overflow is not going to happen, we can just do the addition. And notice here that at the function type, we also track exceptions. And I think this is a feature also that Java has in a certain way, where you also track at the type level of what kind of exceptions can occur. But another notion of exceptions is like, we don't just raise the exceptions, but we can also install handlers to service the errors. So for instance, we have this complex code where we're installing a handler, this handle construct, on some kind of a complex code that somewhere we call this add function, right? And our handler, we install the handler in our computation here, we're saying that we want to capture the exception. If an overflow exception occurs, we want to just print overflow has been detected and just return nothing. I don't know what else to do with it. Just stop the computation and return nothing. Otherwise, if the computation here runs fine, we're just going to return the volume. But so the idea with exception handlers is that we raise an exception, then we can handle the exception, we can capture the exception, and at the point where you capture the exception, you run some other kind of code somehow maybe recover from the exception. But the key problem, or maybe limitation of exception handlers, is that they do not allow us to return, to continue executions. For instance, what if we wanted to capture an exception and service the error in a way, but then let that expression, let that program that raised the exception to continue? For instance, in this add example, we might want to say, when overflow occurs, just return the maximum unit max. We don't care if it's any values higher than that as a result of add. So we could envision some kind of a handler construct where in the case when an overflow occurs, like before, you see there's an extra argument k, like before k didn't exist. Now we get an extra argument k. With this k is some kind of like a special function that allows us to continue execution of the program that raised the exception in the first place. And then we can also call it the argument that we call it, so allows somehow to communicate with the program that raised the exception. So this kind of notion now, if we generalize a bit of exception handlers, and by a way of allowing the program that raises exception to continue it, we're stumbling on the idea of an effect handler. We discovered effect handlers. And it turns out that effect handlers, because by allowing this ability to continue execution, they are powerful enough not just to model or to represent exceptional behavior, but also lots of other kind of programming abstractions. For instance, we can now when we use different terminology. We talk about effects and handlers instead of just exceptions, where exceptions is one instant of an effect, but we also can represent non-deterministic computations, cooperative concurrency. For instance, if you've seen async and await from JavaScript and Python, this kind of things, all these things, we can encode them using effect handlers or stateful computations and everything. So the effect handlers are a very powerful construct that we can, if you can envision a language with just effect handlers, it's very minimal. It just has this, and then we can encode all these kinds of more other features, such as cooperative concurrency as derived construct. So that's pretty cool, pretty nice. And there's a lot of research that's been happening nowadays on effects and handlers. And they have been retrofitted in OCaml, if you worked with OCaml before, but also lots of other research languages such as Lynx, Coca, F. So there's plenty of ways to play around with them if you want. But let me make it a bit more concrete of what exactly these things are. And first of all, we need a way to, when we talk about effects and handlers, we need some effects need to come from somewhere in the first place, right? And the terminology to be used here is through so-called operations, such as this choose. So choose is an operation which has an accompanying signature, and it takes a unit and then it returns a Boolean. And we can use this choose effect to define this choose int effectful function. What this choose int effectful function does, it takes two arguments, takes two integers, and calls the effect choose, and according to the result of the choose, you returns either the first or the second number. Right. So, and you see here that again at the function type, we have the function choose int, because it's an effective function, is given an effect type. So it's track at the function type. You also track what kind of effects it produces. And we need to track this, actually. It's useful to track these things because choose doesn't have any intrinsic semantics into it. It's not an operation that is defined. It's just a syntactic thing. To give meaning to choose, we rely on handlers. So now handlers, effect handlers, do not just represent capturing exceptional behavior, but handlers are also, in the case of effect handlers, give meaning to our effects. What do I mean by that? For instance, if you want to say, okay, whenever you've performed a choose effect, I want you to always respond with true, the true value. And the way we can specify this is using a handler, such as this choose first handler that I call it. And the way to say that we want to continue the execution with the value true is by calling this k function, this special function that I've told you from before. And the continuation, this k represents the remaining unevaluated program. For instance, in the case of the choose int, k represents this dashed line, this the remaining unevaluated part of the program. And the value that we call with the true takes the place of this do choose expression. So a handler, the way we give semantics, the main idea here, the way we give semantics to what effects are is using handlers. And these handlers can communicate with the rest of the program, with the program that raises the effect in the first place. Let's make it a bit more concrete. Let's quickly step through this program and see how it executes. So for instance, we have this handle, we have this choose int function, and we want to say, well, whenever you get a choose effect, you want to reply with true. And the way this is executed is, firstly, we unwrap what it means for choose int. At this point, we call the continuation, we call the effect handler, and k here represents this part of the expression, represents the unevaluated part of the expression. So we call k here, and we result with this. We call the branch, we call k with true. K takes the place of we substitute what k really is, and we call true. And if we quickly step through this, we get 1. So long story short is that handlers give meaning to semantics, they give meaning to operations. And the way that they give meaning is by using this kind of continuation, by communicating the right way to this function. Alternatively, we could say, well, what if we, instead of just choosing the first value, what if we want to choose both values? So call a continuation with both values and collect all the possible results in a list. So this is interesting. So now instead of just replying with some kind of fixed value to choose, we can continue the execution with both values and then collect all the possible evaluations in a list. And in this case, k, the continuation, the special argument that allows us to continue execution, is called a multi-shot continuation because we call it twice. Whereas in this case, it was called in this case, k was called a one-shot continuation because we call it just once. And this is some terminology that I would like you to keep at the back of your head. Okay, and if we quickly step through just like before, what happens is just like before, we unwrap the definition of choose int, then we call the k, we substitute k with the unevaluated part of the expression, we do some simple computation, and we result in 1 and 2. Okay, so what is the problem statement? Now we have seen I've told you what substructural type systems are, I've told you what effect systems and effect handlers are. What is the problem now? Okay, so the problem is, what if we wanted to combine these two? What if we want to have a language? This also has these deallocatable references, so references that we can allocate and free. So that would mean that we need a substructural type system. Otherwise, we're going to have all these memory errors. Now, we also want to have like effect handlers because effect handlers are nice. They make our language expressive and we can do cool things with them. And if we had envisioned like naively just put these things together, things break. And what do I mean by that? Take this bat function, which takes a reference and a fine reference. So you're still having like revisioning that we are in a realm of a substructural type system. And we call this effect choose int, that the result, we bind it to x. And then what we do afterwards, we free the reference r, and then we do the addition, because freeing r also gives us the previous contents of the reference. Okay, so it's a fine program, right? Because the reference r is really just used at once. So what is the problem here? I mean, in terms of like substructure, what we've seen is we just allocated the we have taken a reference from this as an argument, and then we have just freed once. But if we handle choose, if we say that we install this choose first handler, where we get the first, we always respond to choose with the first value, the true, then everything is fine. You have no memory errors. But if we actually give meaning to choose using a multi-shot handler, such as the collect all handler, where we respond with both Boolean values, well, there we're going to get a double free. And the reason for this is, well, we're going to call the continuation, this k argument in the handler. Well, it's going to respond with both values, both true and false. So we're actually going to get a double free. And the key problem is that references, which you want to treat affinely, substructurally, they are captured in a multi-shot continuation, such as what the remaining, what k represents. And the multi-shot continuation, k in this example, is supposed to be called more than once. So this is the main idea, that whenever we want to have an effect system and a substructural type system, we have to also, there's an extra thing that we have to look out for, that things are not captured, what things are captured in continuations. So I've shown you that the problem is if we naively combine these two, we can still break the memory safety guarantees. We still get a double free. But what is the solution to this thing? And the solution is to make the effect system also substructural aware, meaning that we have to also distinguish between one-shot and multi-shot effects. Okay, what do I mean by that? The idea is that just put the brackets in the right place. It shouldn't just be a substructural type and effect system, but the substructurality should apply to both the types and the effects. So in the effect system, we should also have two different kinds of effects. We should have a so-called notion of a one-shot effect and of a multi-shot effect. And what this system would do is whenever we type something as a one-shot effect, then we can only handle it in a one-shot way. So we can only install a handler such as choose first, where we only call the continuation this k once. Whereas if in a multi-shot effect, then we can do whatever we want. Then we can say we can install the collect all handler, because the continuation, this k can call it more than once. And also there's the notion of stop forbidding references from being captured in multi-shot continuation. But as an example, the bad function is not typable from before, because we have called, because we choose here is a multi-shot effect. So you can see this is the notation for the multi-shot effect. So choose here in the bad is called the multi-shot effect. So it means that we can call if we install a handler to it, we can call the continuation k more than once. And this is a no-go, because then we captured the continuation, the remaining unevaluated part, as you can see here from the this part. This part represents the unevaluated expression. Captures references. So this is another guarantee that the type shares to have. But instead, to make this a well-typed program, we need to give choose. We need to mark it as a one-shot effect. So then with this distinction now that we have this kind of like distinction between one-shot and multi-shot effects, by giving choose a one-shot signature, we restrict ourselves. We say that we can only install one-shot handlers such as choose first. So now with using this kind of like extra restrictions that we have placed out, we can be sound, we can still have all our memory safety guarantees and everything. Okay. Hopefully you got a main idea on how we are like substructural type systems, effect systems, how we can combine them, what are the problems that occur when we combine them. What is the time, by the way, that how much time do I have? Where is Codrin? All right, I'll just imagine 5-10 minutes. Okay, so lastly, what I want to talk about is, I think, so-called semantic typing. And the idea is, okay, we have this nice fancy type system and effect system, and we say like, we have devised it in such a way such that we get some kind of guarantees that there are no memory errors in it and whatever. But how do we formally prove that this is indeed the case, that what we claim that this type system does is indeed the case? And the approach that that I will show you is an approach, it's a proof technique called semantic typing. I don't expect you, this is a very big, complicated technique. I don't expect you to understand really what this thing is about, but just get an intuition, maybe. So don't worry if you get lost, is what I'm saying. But what we want to show here is if we have a well-typed expression, this is the typing judgment, then we want to prove a lemma, no, it's not a lemma, it's a theorem, a type safety theorem that tells us, okay, this expression, this program is actually safe. What we mean by it being safe, we want to say that, okay, if you evaluate this program E, you're not going to get your usual type errors, such as calling true with 0. But at the end, also, we want to say that no effects are left unhandled, meaning that this angle brackets here shows that no observable effects occur. So the safety should also tell us that we are accurately tracking what kind of effects are producing. So we can't just suddenly say we get an error because our typing judgment says that this is an unaffectable expression. And importantly, we also want to ensure that these memory errors don't occur, right? I mean, this was the whole motivation, that we don't get this use after free, these double free errors and everything, and that these things do not happen. And to prove this lemma, theorem, sorry, it's not very, well, it's not very easy to prove, let's just say. There are different approaches. Usually, if you're considering a simpler system, you have the so-called syntactic type soundness proofs, which there's two theorems that you prove, progress and preservation. You might learn about it, or if you have, good. But usually, there's a notion of syntactic type soundness, which is a bit easier to grasp and easier to use, but it's a bit limited. It's not very powerful. And if you go to a system such as the one I'm presenting you, with even more features, then you really cannot use this syntactic approach, and you need to use a more semantic approach. And in the semantic approach, what you do is that instead of working just with syntax and typing derivation and everything, you give meaning to this, to your terms. You give meaning to your types and your effects and everything, and your typing judgments. You interpret it in some kind of a logic. And the idea is in semantic typing, you prove these two theorems, this fundamental theorem and this adequacy theorem, where the fundamental theorem takes a typing judgment and interprets it in some kind of a logic. The logic here is a separation logic. It's a special kind of a program logic that allows you to reason about your programs as well. And then by interpreting in this kind of semantic way, the semantic typing judgment, so this angle brackets over the typing judgment, which is some kind of a proposition in our logic. This proposition, by the way we define this proposition, we also get via adequacy, that we also get safety. Okay, so what is exactly, how does this logic look like? And this logic, which is the iris separation logic, is a separation logic. And it's a separation logic also allows you to reason about programs that handle references. And the idea is you have this kind of like higher order logic at the top row with your disjunction, conjunctions. But you also have separation logic, you also have other propositions that allow you to reason, to model state and reason about states. And you also have other modalities, which I'm not going to talk about. But if you want, this iris work has been highly successful. There are lots of papers about it. And because it's very powerful logic. And it's also always mechanized in the ROC proof assistance and everything. But what do we mean by separation logic? So let me focus a little bit, get intuition, give you some kind of intuition of what these propositions are. And the idea of this logic, because it's separation logic, is that it also has a notion of a resource, of a heap, of like of what our memory looks like. And the way we have this L points to V, so it's a proposition that tells us, okay, at this point, the memory location L is allocated with a value. We also have this P star Q, which is called the separating conjunction, which allows us to reason modularly about our program by saying that P and Q must reference distinct parts of the memory. We also have the notion of a resource-aware implication, but also crucially, we have this WP called weakest precondition, which is another proposition in our logic, which just says that if this proposition is true, then we have three guarantees. We have that expression E is either going to diverge or it will terminate. If it terminates, the resulting phi, which is a predicate, will hold on the resulting value, and that the effects that this expression produces satisfy a certain kind of protocol. Now, okay, so I haven't defined all these things, but the idea is that WP is some kind of a proposition that says E is actually a safe expression and obeys certain things, right? And then iris is operational logic, which models away your heap, which allows you to reason about a stateful computation. And you have this kind of like proof rules with using this WP and everything that allow you to reason about your program. It's a program logic. So for instance, in the WP if rule, to show that the weakest precondition of the if true expression, it's enough to know that the E1 expression is itself satisfies WP and everything. And using this kind of program logic, so this program logic allows us to reason about our programs, say what kind of things hold in our programs, use it by composing these proof rules. And using this logic, we interpret our types and our effects and our judgments. We give what it means for these types and these signatures and everything. I don't expect you to really understand what these things mean, but the idea is that we map what the types mean in our language to some kind of predicates, to some things in our logic. And our typing judgments, they are defined also using this kind of like WP weakest precondition and everything. So now we have interpreted our types, our effect signatures in our logic and everything. And the main work that we really need to do here is that, well, we have mapped every, oh, now we have 10 minutes. Oh, I am way, okay. So, well, in that case, I should slow down. 10 minutes from before. Okay. Well, this is my last slide. All right. So the real work is that we have this typing judgment, this syntactic typing judgment, and we use this fundamental lemma, interpret it in our logic. And what we have to do is that we have to show that each typing rule, such as the abs typing rule, becomes a lemma that we prove in our logic. Because a semantic typing judgment, so a typing judgment with this double quotes, not double quotes, uncle brackets, no, they're not called uncle brackets, the Scott brackets, they are propositions in our logic. So a typing rule becomes a lemma that we show that each of our premises is a proposition, and the conclusion is what we want to show. And that's where the real work lies in, improving that these things hold. Okay, so this is the end. So the main takeaway is as follows, is that we have, when we're talking about deallocatable references, we want to have a substructural type system, such as I've showed you some kind of like a very simple Rust-like type system. And that guarantees that we don't get these memory errors. And we also have algebraic effects and handlers, which are quite powerful, and we can implement lots of abstractions using them. And if we want to combine both of them, then we need to be careful. How are we going to combine them? Specifically, we have to be substructural also on the types, but also the effects. So we have to have a notion of a one-shot effect, of a multi-shot effect. And lastly, to prove all these things, that the things that we set out that they hold, the things that we want to hold, to prove really that this is indeed the case, we use the approach of semantic typing, which is a quite powerful approach. And if you want to read more about this, you can talk to me, or you can also read the paper with this title. Yes, this is the end. Do you have any questions? Oh, immediately. Yes, 1 minute. Should I just take the? Oh, right. You need the yeah.
So hello, so you talked about double free and free use after free. What about memory leaks?
Yep.
Can you ensure that there are no memory leaks?
So with memory leaks, there's a notion of affine and linear. I've shown you affine things, which affine means, which the way I've defined them here. Oops. Back. No, yeah. With affine, the slogan is you must use references at most once. This is what affine means. If you're linear, means you have to use the references exactly once. And using them exactly once also gets you that there are no memory leaks occur. But in practice, it's not that using linear things is not that it's not very programmer friendly. Let's just say. I mean, I could have given you an example of linear references, which you also get that there are no memory leaks, but unless you do some smart things such as like what Rust does, which kind of like inserts this automatically, these drop operations and everything. But the idea is, what I'm trying to say, you just have to replace affine with linear, and then you get also memory leaks, the absence of memory leaks.
And something that is related pretty closely, you introduced free and read. How can you use read and then free, given that references must be used at most once? So
that's a good point indeed. So this is the point where if you really want to make it an actual language, you have to use something like Rust. You need something more fancier, but a quick solution to this is your read operation doesn't just return the value, but also returns you a new reference kind of thing. It's not a new reference, it's the same thing, but it's what allows you to use it afterwards as well. Yep.
Well, first of all, thank you for the talk. It was really, really good. I was wondering if instead of using affine references, if you were, for example, ref counting, would multi-shot continuations then be possible at all?
Right. So ref counting or a garbage collection or this kind of things, that's where you don't have freeing operation. Freeing the reference is not part of it's not the programmer responsibility. It's already done by the runtime system of the language. In that case, you still have problems, but not specifically this kind of problem, because the reference counting does this kind of like implicitly knows how many references there are. I mean, I imagine a reference counter will be somewhat implemented in a way that it should be, but there are other problems regarding this. So basically, you would move the program a little bit in the implementation side of the reference counting. So then you would have to somehow make sure that whenever you're doing, I don't think there's not even that much to do there. I think it's already clear that should happen. But what I want to say, the big problem is that there you switched the problem of doing a double free or use after free. The problem also becomes of what kind of optimizations can occur, which is a more subtle problem, but this is also in the paper, if you would like to read it, is where it's a problem of even if you don't have deallocatable references, so you just have references that you can allocate and you can update and everything, it is you don't need to treat these references substructurally necessarily, but you have to, not all the optimizations that you can apply when you have just one-shot effects. If you have multi-shot effects, a lot of optimization no longer hold. So there's still a use case there to have substructural type and effect system. Just saying is that the problem then is a bit more complicated, but there's still problems with that as well.
Thank you.
Yep.
Hello.
Thank you for the talk. I've got a question regarding mix the affine type system with like normal type system. Because like for example in C++ you could mix a raw pointer with and then convert that into a shared pointer, which you're converting something that you can use as many times as you want into something that's more of like similar to affine, I guess. Well, like for example, if you convert something from like unique pointer, for example, and
C, one minute. So C++ is not substructural. Right? But what do you mean? You can convert a raw pointer to?
Like, does this support like mixing normal types with affine types, for example? Like, if I want to take control of something that can be used as many times as I want into something that's affine type, does that work? Like, does it handle these cases?
So whether we can combine, what do we envision C++ language with affine types is, or whether you can convert an affine type to a normal type?
No, normal type to affine type.
So whether you can do this translation?
Yeah.
What do you mean by convert it?
Because
like you mean like you think like subtyping?
Kind of like can we just control like from a normal type, because we can use that as many times as I want. But at some point, say that we want to, at this occasion, we figure that we want to use it one more time and then we deallocate it. Can we just handle those cases?
Well, so I'm not 100% sure what you have in mind, but what I can say about this is that if you can use things normally, you can just then say, you know what, I'm going to switch to this being affine, because you don't know, maybe there are different aliases of this thing somewhere else in the code that you're not tracking. So doing this transition subtype from a normal type to an affine type is not a sound thing to do. Okay. The other way it works, you can, if you have an affine type, oh no. Oh, wait a minute. Oh, you are right. Yes. Okay. Yes, you can. Okay, sorry. You can do if you have a normal type, you can treat it affinely. It's perfectly fine, given that this thing is really not something that has to be tracked affinely, but you can annotate. You can kind of like think that is affinely. Then you could say, you know what, at this point. So what I mean is, if you have a type that can be used, the inhabitants of the type can be used any number of times, it's perfectly fine to put an extra restriction and say you can use it at most once. But that thing to begin with in the first place is not really an affine values. Sorry, affine values. We could talk more about this.
Thank you.
We have time for one more question.
What about defining free as an effect?
Defining free as an effect. Well, so, right. Okay. So then there are different approaches here. But you can have, for instance, I said that one of the examples is having stateful computations, right? So effects can represent state, such as getting state, allocation of state. But here, the two things are different. We have this kind of like references, which are not part of your user-defined effects. So they live in a little bit of a different parts of your code. And this is usually the case, for instance, with OCalm, which is done mostly for optimization purposes. But you can envision also a language where your stateful allocation, the alloc, free, read, everything are just effects. So the question is whether we can do that. I guess I have to think about it. I don't think it's gonna solve anything specifically. It depends what you mean by. Yeah, let me think about it a bit. But so you're saying having the alloc and the free and everything as being effects, right? And the problem is whether we have double frees and everything. You will still have the same problem, because there is the you probably have the same problem because you allocate the reference, the effect will return you some kind of an identifier to that location that you have allocated. But then how can you ensure that your effect, you don't call the effect free more than once? Using some kind of a substructural thing, indeed, but yeah, it's the same problem. I mean, I would have to discuss a little problem, but I think it's with what the specific interpretation of what you mean having now, it's not really.
But what makes it the responsibility of one defining the effect handler?
What is the responsibility? What?
As in, the effect handler is the thing that ensures there's no double free.
Yeah, but the problem is that you would have to distinguish between the kind of things that you, the thing that you allocate. You get some kind of an identifier, and you have to ensure that the free operation on that same identifier is not performed more than once, right? You can implement of course, you can implement a smart handler that checks, have I done this freeing from before? Have I done this, kind of like it keeps track of all the frees, and then you can get you get the absence of this thing. But what I'm saying is, unless you want to make a handler that is aware of what things have been allocated from before and keeps track of everything, so that you can ensure that no use of the free or double free happens. Unless you do this kind of approach, there's not a clear way on how to devise some kind of like a substructural system that you don't necessarily have to do the checking or the keeping track, all this bookkeeping from beforehand, but still get the same guarantees. There, I think if you want to just keep track that this thing doesn't happen using only your type system, I think there still probably is going to have the same problem. But then you have to also see what exactly do you mean by these things.
Thank you.